So this set of videos is taking the idea of equilibrium and applying it to the solubility of ionic compounds, which is referred to as solubility equilibria, or the constant is referred to as Ksp. So just as a quick review, when a salt is initially put in water, so you've got the alternating cations and anions, remember that the dissolving process is actually an example of equilibrium because the ions will start to separate. But if the attractions between the ions are strong enough, you can establish equilibrium. So the cations and the anions are attracted to each other with a certain amount of strength, and that strength kind of competes with the attraction that it has to the water molecules, the hydration idea. And so the strength, obviously, what controls how much is going to dissociate is obviously Coulomb's law, the idea of calculating the lattice energy. And like we said, the ions are also attracted to water, so the water molecules start to pull some of the ions off, but you wind up establishing, in many cases, an equilibrium in which some of the solid is dissolved as ions, but some of it stays together. And if that's the case, you wind up with a solubility equilibrium. So at first, like I said, the only process that's occurring is the dissociation of the ions from the salt. But at some point, those ions reach a saturation point, or a point where there's enough ions in solution. The attraction between the ions in solution and the crystal is strong enough that those crystals or those ions are start to be pulled back to the crystal. So eventually you wind up with the rate of dissociation equaling the rate of precipitation, or the rate of recombination. And that's when you have equilibrium. So the solution has now reached the point of saturation, and you have equilibrium. So equilibrium can happen with any sort of salt as long as you have enough solid in there. For the salts that we've talked about previously as being insoluble, it just means that their equilibrium constant is really, really, really small. Basically, it means that it doesn't take many ions in solution to get that equilibrium established. So that's what this whole section of the unit is going to focus on, that idea of the equilibrium between the ions dissociating and the ions coming back together. And so, like we said, this kind of just repeats the idea with a nice visual. A saturated solution, there's no change in the amount of solid in the precipitate. There's no change in the amount of ions in solution because you have an equal transition between the crystal and the dissociated ions. All right, so let's take a little bit closer look at this idea of solubility equilibrium. So we're going to use silver sulfate as our example. So silver sulfate is supposed to be insoluble. To a certain extent, it's going to dissolve to dissociate into ions. And when the solution is saturated, it's going to establish this equilibrium. Now, this equilibrium, you've got a reasonable amount of solid that exists when you hit that equilibrium point. So we've always considered silver sulfate to be reasonably insoluble, but some of it actually does dissociate. So that's what the Ksp, the solubility equilibrium, is going to talk about. So again, since we can establish equilibrium, we can write an equilibrium expression. We can say that Ksp is equal to, so now reactants on the bottom, products on the top. This is a solid, so he's not in the dissociation equation at all. We only have the two ions. We got to square silver because there's two silver ions. So this is really the equilibrium expression for the dissolving of silver sulfate in water. Again, notice that silver sulfate's left out because it is a solid. And so the K, just like in first year we learned about Kw and Ka and Kb, this K becomes Ksp, which stands for solubility product, because all we're really doing is multiplying the concentrations of the two ions by each other. So solubility product, how much is actually dissolved in water, is the solubility, and we're multiplying them together, Ksp. So this Ksp represents the constant for any ionic substance when it dissociates in water. If the Ksp is really big, that means you have a substance that's pretty darn soluble. If the Ksp is really small, that means that you have a relatively insoluble substance. So at this point, nothing is completely insoluble. It all dissolves to a tiny, tiny extent. So when you write the solubility product expression, remember that you've got to use the balanced equation, showing its dissociation equation in water. You're going to take the Ksp expression and write that idea from it. So if I have something like nickel sulfide dissolving in water, here's my dissociation equation. I've got 1 ion to 1 ion, and so my Ksp is simply going to look like that. However, iron 3 hydroxide, I've got 3 hydroxides. So when I write the Ksp expression, I need to make sure that I cube the OH minus concentration. Here are some examples of Ksp values. They are experimentally determined, so depending upon what table you look at, the values are going to be slightly different. The powers, the exponents should be the same, but the decimal part may be a little bit different. Notice that aluminum hydroxide is very insoluble because it's got a very small Ksp, as opposed to something like lead 2 chloride or silver sulfate, which has listed in the solubility rules that we've seen before, slightly soluble, or moderately soluble, because it's got a reasonably large Ksp. For something that's completely soluble or very, very, very soluble, the Ksp is going to be even higher. All right, so let's get into all these calculations. The College Board loves Ksp questions on the AP exam, so I would almost 100% guarantee you that you're going to see something with Ksp. So you want to make sure you're comfortable solving these kinds of problems. So something very simple to start off with. We want to calculate the Ksp of silver chromate. Okay, so how much of it actually dissociates? That's what we want to know. Of all of the stuff that we put in water, how much of it has actually dissociated, and how does that control our Ksp? Well, in this case, with a saturated solution, we know we've established equilibrium. So at this point of equilibrium, we've been able to measure that the silver ion concentration is 1.34 times 10 to the negative 4 molar. So we're going to use that in an ice chart. Actually, we don't even need an ice chart in this case because we're already at equilibrium. So this is the equilibrium concentration. So we know that the silver ion concentration is 1.3 times 10 to the negative 4. Okay, but to figure out the chromate ion concentration, the ice chart is useful to kind of think backwards. So we know that this value is actually equal to 2x because we have 2 silvers, to 1 chromate. So 1.3 times 10 to the negative 4 is actually 2x, which means chromate is half of that, or 6.5 times 10 to the negative 5th. So now that we know the two concentrations at equilibrium, we can put those numbers into the equilibrium expression. Don't forget, we still have to, even though this number is double, we still have to square it in the expression. You wind up with a value that is 1.1 times 10 to the negative 12 for the Ksp. So that's reasonably small. Okay, so again, if you are given the concentration of an ion at equilibrium, you can use an ice chart to figure out what the other equilibrium concentrations are and plug that into the equilibrium expression. It's as simple as that. So now let's say that we want to calculate it a little bit of a different way. We want to calculate Ksp a little bit of a different way. We're told that the solubility of silver sulfate is 0.0014 moles per liter. What that's telling us is that this is the amount of silver sulfate that actually dissociated. Okay, so this is my minus x. So now I got to keep that in mind. In my ice chart, That's my minus x, or in this case, I made it an S for solubility. That's my minus S. So to figure out the two concentrations, I've got to remember what the change ratio is. I'm losing this much stuff, which means I'm gaining an equal amount of sulfate ion, but I'm gaining twice that amount of silver ion. So again, if you think I'm going to keep the S's in there because it makes things a little cleaner, really what you're doing is you're squaring the 2s and you're multiplying it by s. So really what you're doing is just taking 4s cubed. So now that I know that s is that value, it's very simple to just plug in the numbers, and I get 1.2 times 10 to the negative 5th. Okay, so two different ways to approach the idea of figuring out what the value of Ksp is. Make sure that you understand the difference. Make sure you understand what piece of information you're given in that question. Because in some cases, like in this case, the value that you're given is how much of the solid dissociated. In the first example, we were given how much ion we had at equilibrium. So we already had the 2s value in that question before. This messes some kids up, so you got to really, really be careful about what piece of information you've actually been provided. Okay, so I think we're going to pause here. We'll go on to the second part of the video for the second idea.